Hi students, welcome back to this tutorial. In this video, we can consider some more examples regarding this lossless joint decomposition. Okay, so these are the conditions, three different conditions that we must follow in order to check or in order to make a decomposition as lossless joint. Okay, so just revise this point. Now consider one example. This R is a relation which is given with attributes V, W, X, Y and Z. And these are the functional dependencies over this relation R. Z implies Y implies Z, X implies Y and V, VW derives X. And the decomposition is like this: VW and YZ. Two different decomposition. Okay, the task is to check whether this decomposition is lossless joint decomposition or not. So these are the three conditions we want to check. So we can go for condition 1 first. So here, while performing the union over these two decomposition, we get a result or resultant attribute set like this: V, W, Y and Z. This is not equal to the set of attributes of our given relation R, right? Because the attribute X of relation R is missing here. Means the condition 1, the first condition itself is not satisfied here. So we can stop here and directly conclude that this particular decomposition is not lossless joint decomposition. Okay, the first condition itself is violated here. So we don't want to check the remaining conditions over the given decomposition. We can directly conclude in this equation this is a lossless joint decomposition. Okay, so consider one more example. The same relation with the same set of dependencies, and the decomposition is like this: two different decomposition V, W, X, and the second composition Y and Z. The conditions are listed here. So the first condition, we need to check the union of these two decomposition with the attribute set of our given relation R first. So here the union is V, W, X, Y and Z. This comes unmatched with the attribute set of relation R. So the condition 1 is satisfied. Okay, so now we can go for condition 2. Now check, there exists any common attribute between these two relation? No, here we have V, W and X, and here we have Y and Z. There exists no common attribute in these two, right? So condition 2 is not satisfied because no common attribute is present. Now we can stop checking and conclude that this composition is, or this decomposition is not lossless joint decomposition. Okay, so one more question. The same relation, same set of dependencies. Okay, and the decomposition is like this: V, W in one set, W, X, Y set in other set, right? So these are the conditions again listed here. First, go for condition 1. So the union of these two attribute set form V, W, X, Y, Z exactly comes in match with the attribute set of relation R. So condition 1 is satisfied here. Okay, next go for condition 2. Here we have the attribute W, which is common for both this decomposition. W is common attribute in these two decomposition. So condition 2 is again satisfied. So go for condition 3. What is that? We need to check whether this common attribute W is a candidate key of any of this decomposition. Okay, for checking that, what we want to do, we want to take the closure of W. The closure of W is W itself. We want to calculate or we want to find out the closure of W with respect to the given set of dependencies here. From this, it is clear that the closure of W is W itself. Here we have no dependencies that is deriving from W. So the closure of W is W alone. So using this W, first consider this decomposition. This W can't derive V. Why? Because this W can derive this V. Why? Because this V is not present in this closure set of W. So this W is not a candidate key of this decomposition. But we can stop here. We need to consider the same in other composition or other decomposition also. Here again we have different attributes W, X, Y and Z. Right? But using this W in this closure we have no other attribute. Means this X, Y and Z. This attribute values can't derived by this attribute W. So W is not a candidate key in this decomposition also. Okay, so it is clear that now we can conclude this particular decomposition is not a lossless join decomposition. So this is the method if we are asked with a question like this. That is, a relation is given and set of dependencies over that relation is given and also the decomposition. And you are asked to find whether that particular decomposition is lossless join or lossless join decomposition or not. You are asked to find whether that given decomposition is lossless join decomposition or not. So in that case we want to follow or we want to proceed like this. Okay, in order to check whether the common attribute is a candidate key of any of these decomposition, what we want to do, we want to take the closure of that particular common attribute with respect to the given set of dependencies. Based on that, we can identify whether this common attribute form a candidate key of any of this decomposition. Here, this W is not a candidate key of any of this composition. So, we can conclude that this is not a lossless join decomposition. Consider another question. R with the same set of dependency, but the decomposition is like this. Okay, so conditions are listed here. So the first condition, the union of these attributes V, W, X, Y and Z. This is exactly the attribute list of R. So condition 1 is satisfied. Right, so go for condition 2. Here exists a common attribute X between these two decomposition. X is common. So condition 2 is satisfied. Again, check whether, so condition 2 is satisfied, we want to go for condition 3. So we want to check whether this X is a candidate key of any of these decomposition. Okay, so for that what we want to do, we want to find the closure of X with respect to the set of dependencies given here. So X closure is X is directly added to the closure set, then Y, then V. Further, Y can derive Z and Z can derive Y. Y is already present here. So this is the final closure set of X. Okay, so now using this closure set, just analyze these two decompositions separately. Here, using this X can derive the value of V, or now we want to check whether this X can derive the value of V and W. Is it possible? Here, in this closure set, V is present. Means X can derive the value of attribute V. Right? But W is not present in this closure. Means X can't derive. Using x value alone, we can't derive the value of w here. Means x is not a candidate key of this particular decomposition. But we can stop here because we have one more decomposition. We want to check in this decomposition also. Okay, so x and y and z are present here in this closure set. Means x can derive the value of y and z. X can derive value of y and z. Means this x form a candidate key of this particular decomposition, because using the value of x we can derive all other attribute values of this particular decomposition. It means x is a candidate key of this particular decomposition. Condition 3 is satisfied. Here we want this particular common attribute as a candidate key of any of these two decomposition. So here it satisfied condition 3, means x become a candidate key of this particular decomposition. So condition 3 is satisfied. So finally we can conclude that this particular decomposition is a lossless joint decomposition. This is an example for lossless joint decomposition. Okay, now we can consider a different example, somewhat complex example. Okay, this one is a gate question. Previous year gate question, a relation is like this and the functional dependencies are listed here, and the decomposition here it is R1, R2 and R3. Three different decompositions are given here. Instead of 2, here we have 3 different decomposition, and the task is to check whether this decomposition R1, R2, R3 is lossless joint decomposition or not. Okay, so we want to go for our first condition. Union of these 3 attribute list is equal to the attribute list of R or not. Here attribute of R1 union attribute of R2 union attribute of R3 is equal to attribute of R or not. So A, B, C and D, all attributes are distributed over here this decompositions. Attributes of R is distributed here in this R1, R2 and R3. So condition 1 is satisfied here. No attribute is missing. So condition 1 is satisfied. So go for condition 2. Okay, here we have 3 different decomposition. Now we want to check whether a common attribute exists here or not. For that we need to consider a pair of decomposition. That means we need to check R1 with R2 or R1 with R3 or R2 with R3. We need a common attribute between any of the 2 such decomposition. So we can start with R1 and R2 here. So find R attribute of R1 intersection R attribute of R2. We can consider any such pair. Okay, this intersection actually work with 2 different set. This is a binary operation. So work with 2 different set. So we can consider any 2 pair. So we can start with this R1 and R2 here. Okay, so here exists a common attribute which is B. So in R1 and R2 the common attribute is B. So in R1 and R2, in these 2 decomposition, condition 2 is satisfied. So proceed with these 2 set R1 and R2. We need to check condition 3 also. Okay, in this time we can keep this R3 here. We need to concentrate over this R1 and R2 alone now. Okay, so condition 2 is valid for R1 and R2. So go for condition 3 over this R1 and R2. That means we need to check whether this common attribute B is a candidate key of any of this relation R1, R2. For that we want to check or we want to find out the closure of B first using this given set of dependencies. B closure is B, D derives C, added with the closure set, C derives D, D added with the closure set, D derives A also added with the closure set. Okay, so using this closure set, now consider the first decomposition R1AB. The closure of B contains B and A. That means using the value of B, we can derive the values of A uniquely. So B is a candidate key here. That is enough for our third case. But we can also consider R2 also. So in R2, here these are the attribute B and C. In this closure set, we have B and C. That means using the value of B, we can derive the values of C uniquely. Here in this decomposition R2 means B become a candidate key here also. In this case, in this particular example, this B is a candidate key for R1 and R2 also. Fortunately, this B become a candidate key for R1 and R2. We need this condition valid for any one of this R1 or R2, but in this particular example, B become candidate key for both R1 and R2. This is a valid case again. So condition 3 is again satisfied. So now we can consider that now we can't stop here, because here we have one more decomposition R3. Okay, here condition 3 is valid up to condition 3. All the conditions are valid for R1 and R2. But we can stop here. Why? Because here we have one more decomposition R3 we want to consider along with this R1 and R2. Okay, for that what we want to do here, in the previous slide it is clear that R1 and R2 together satisfy the condition for lossless joint decomposition. Now we can combine these two together and form R12. R12 contain attributes like A, B and C, because these two decomposition together satisfy lossless joint decomposition. So this combined relation R12 we need to consider with this remaining decomposition R3 of C, D. Okay, so the first condition is already satisfied. Okay, so here we have any common attribute between this R12 with R3. Here C is a common attribute. The condition 2 again is satisfied. And we want to check the condition 3. That is, we want to check whether this C is a candidate key of any of this relation R12 or R3. For that, what we want to do, we want to find out the closure of C first based on the given dependencies. So in the closure set, C is directly added in the list, then C derive D, D is also added, D derives A is added, A derives B, B is also added. So this is the final closure set of C. Right. So using this closure set, now we can check whether this C act as a candidate key here in this R12 or R3. In this R12, the attributes are A, B and C. This A, B and C present here in this closure set. Means using the value of C, we can derive the value of A and B uniquely. Right? Because these A and B present here in this closure set of C. That indicate using the value of C, we can derive the value of A and B uniquely here in this relation R12. Means this C form a candidate key here in this relation R12. Okay, that is enough for our third condition. But here we can consider this R3 also. Okay, so in this R3, here we have attributes C and D. Right, so this D again present in this closure set of C. This indicate using the value of C, we can derive values of D uniquely. That means this C form a candidate key here also in this decomposition R3. So fortunately, this C form a candidate key for both this relation here. This is a valid case. And we can conclude that condition 3 is also valid here. Okay, so now we can finally conclude. Here we have no other decomposition left without checking. Okay, so now we can finally conclude that this particular example is a lossless joint decomposition. Okay, so if we are given with 3 or more number of decomposition, we need to check the condition pairwise, because this intersection, join operation, etc. are actually binary operations. Okay, binary means that work with two different inputs. So we need to apply this operations over two different decompositions and combine together, and finally conclude that whether it is a lossless joint decomposition or not. Okay, thank you.